Okay, we can start this off. Thanks. So today I wanted to try to explain some of the geometric arguments that show up in the proof of the theorem that I stated at the very end of last lecture. Unfortunately, I would like to say that I would like to explain the proof to you, but it's incredibly fiddly and technical, and I just want to explain the more geometric parts of it. So firstly, I want to introduce a slightly different flavour of space of manifolds. So last time I introduced these spaces of manifolds inside big Euclidean space and so on, with boundary conditions and things like that. And here's a similar thing that I do. So for an open subset of Euclidean space, and theta just like we had last time, so some tangential structure, I want to define the following set. So theta, remember, was something over BOD. And so in particular, by choosing a theta, I've chosen a D. It's called psi theta of U. And as a set, it's the following rather nice thing. It's the set of subsets of U such that X is a d-dimensional smooth submanifold. And it should be, doesn't have to be compact, but it should be closed as a topological subspace. So you shouldn't have silly accumulation happening. Closed as a subspace, comma, a theta structure on it. Okay? And I really mean that the manifolds don't have to be compact. So if U is my thing like this, I can have manifolds that go off to the boundary of U and so on, and they can have compact bits, they can be disconnected. Maybe I make a surface instead of one manifold. Things like that. And they have this theta structure as well, which I won't draw. Okay? So this is a set. It has a topology that I won't define in detail because it's also rather fiddly, but the topology has two important properties. The following two things are continuous in this topology, which I assure you exists. Firstly, if I've got a point in this space, so some manifold, and I have a compactly supported section of its normal model, then pushing the manifold along that section gives a continuous path in this space. So that's what you might think is a reasonable move in a space of manifolds. You wiggle it in a compact bit of it, and that's allowed. So this is allowed.
You don't have any condition on room around your submanifold today. Yesterday there was this one
that they had to be fat.
Yeah.
No. I'll forget about that for now. Yeah.
Okay.
And the second thing that you're allowed to do, which is the slightly more surprising thing, is that suppose I've got, for example, a little compact bit, I can just push it to the right until it falls out of the set. And that gives a continuous path that converges to the empty, in this picture to the empty manifold, the empty submanifold. Okay? And if you think about it, the way you make these two things both happen is that you declare a standard neighbourhood for manifold X to be other manifolds that on a compact set agree with some normal section, some small normal section. And outside of a compact set, they can be wild. And in that sort of topology, this will converge to the empty manifold. Okay? And so there is a topology on this. There is a topology such that these are continuous. And in that topology, phi theta of flank is a sheaf of topological spaces. So if I've got a submanifold of U, I can just intersect it with a subset V, and I get a submanifold of V. And this is a sheaf of topological spaces. Okay? So this is somewhat different in flavour to the sort of manifolds we did last time. Things can be non-compact, they're topological type and change continuously in the space. So So I'm not going to do so much with this definition, but it's very convenient for defining other things. So I'll define some other spaces in terms of this.
The sheaf of topological spaces is just a functor to topological spaces such that the underlying set value functor is a sheaf, or is it more?
No, so the pullback condition should be a pullback in spaces.
But you only require a pullback condition, not anything else.
So it's a sheaf in the category of spaces, yes. So. Sorry? No.
Sorry, I missed the condition on L, so this should lift.
L?
Tangent bundle.
Oh, that.
What makes sense?
No, so remember, so the point of doing this bundle map thing is that you don't have to talk about gas maps and so on. So it just has to be a bundle map. So I guess these things are in Rn, and so you do have a gas map, but I don't want to talk about that.
And you use the topology of the space of bundle maps.
Yeah. Right, and similarly, I don't want to say this. Right, so if so I also have what I call psi theta d minus 1, which is the same sort of thing using d minus 1 manifolds instead of t manifolds. With the same conditions, except that now, of course, we have to make the bundle have the right dimension before we can define the logic map. Okay? So it's the same theta, but I think of it now in d minus 1 manifolds. Okay, so I'm going to use this to define a category where the objects are d minus 1 manifolds with theta structure, looking a bit like this, and the morphisms are d-dimensional cobordisms between them. But I want to be a little bit flexible with what a category is. In particular, if the morphisms are going to be cobordisms, you clearly can't have identities in this category. Okay? You can't have actual identities. There's no actual cobordism that you can glue on and you get the equal manifold back. Okay? So what? So we just talk about categories without identities. That's fine. And the way I want to do that is as follows. So a non-unital topological category C is a pair of things, a pair of spaces called O and M for objects and morphisms, and a load of maps. You have maps called source and target from the morphisms to the objects. And you have a map called product from morphisms cross over the space of objects with morphisms, where we cross here using target and here using source to M, called composition, such that mu is associative in the sense that you can easily imagine. And that's it. That's the topological, non-unital topological category. Okay? Such a thing has a classifying space because it has a nerve that's not a simplicial space anymore, it's a semi-simplicial space. Because you don't have degeneracies, because you don't have units. So this has a nerve embodied in C, which is a semi-simplicial space. And what's it given by? Well, the 0 simplices are just the objects of the category, the 1 simplices are just the morphisms of the category, and the k simplices are the composable k tuples of morphisms of the category. So it's just morphisms cross over objects with morphisms cross over objects. Morphisms, k times, where we do target source all the time. And this is a semi-simplicial space where the face maps are given by here source and target, and here source and target if you happen to be, or rather forgetting morphisms if you happen to be the outer ones, and composing if you happen to be the inner ones. So it's just like the usual formula for the nerve of a group or a category, except that we don't talk about degeneracies. So face maps are by composition. Or dropping. And you have a classifying space, which is the geometric realization of this semi-simplicial space. Yeah?
So the problem is that when you glue the bordisms, and you want to have some constant length of the bordism. Right?
Well, so you want it to be an actual category. So a morphism is an actual manifold. Meaning you have a set, and you have a topology, and you have a sheet full of smooth functions on it. And if you glue on another thing, you've changed the underlying set. So it's not the same manifold ever. There's various ways of messing around and trying to make a category. Just better not doing because, in any case, units play no role whatsoever in looking at those sort of things. Yeah. So it's probably almost a theorem that any way you might have of putting in units into my category of cobordisms will have the same classifying space up to homotopy, and that's what I care about anyway. So that's a general non-unital category. Now I want to define a particular one. This is category of cobordisms. C theta of Rn. So there'll be some Euclidean space around, but then I'll take the limit over all n, so it won't actually depend on which Euclidean space we use. Be the non-unital category with objects the following space. So my objects are going to be elements of this set here. So D-1 manifold with a theta structure that happens to be compact. So there they weren't required to be, but I'm going to ask it to be, and the way I'm going to ask it to be compact is I'm going to ask it to actually lie inside the unit cube. Okay? And because I insisted that X was closed as a topological subspace, that now means it's actually a compact manifold without boundary. And it's topologized as a subspace of that, which I haven't told you the topology for, but we have at least some pictures to bear in mind. And the morphisms the subspace of psi theta r plus Rn. So the morphisms are in one dimension higher of manifolds of the form so that again, in principle, elements of here are allowed to be non-compact in all these different Euclidean directions, but I only want to take ones that are only non-compact in the first direction. So they're bounded in the other n directions. So the manifolds of the form, so this is an Rn, well this is Rn plus 0 in fact, and this is Rn plus T, is on T, and to the left of that, they're just a product manifold. And to the right of this, they're also just a product manifold. And in between there's something. Okay? So the things I've described here are all inside this space. They're manifolds, they're closed to the subset, they have a theta structure which I haven't drawn. And I ask them to be of this form. So they're standard to the left of 0, they're standard to the right of t, and I guess t is part of the data. Said that. And in between there's some cobordism. And in fact, just for technical reasons, I'm going to suppose they're standard slightly to the right of 0 as well, and slightly to the left of t.
Do you want the projection onto the R factor to be proper, or do you have...
So in fact, that's going to be false because I actually want them to be inside R, of course, minus 1, n. So they're non-compact in one direction, but they're compact in the remaining n. So that forces that naturally. Right. So yeah, so the morphisms are pairs of a manifold and a T. T's part of the data. And how is this a category? Well, What are the source and target maps? The source map is you intersect with this slice, and you take that d minus 1 manifold. And the target map is you intersect with that slice, and you take that d minus 1. Okay? That gives you maps to the state of objects. And what are the compositions in this category? Well, let me just draw one. If you want to compose that with, there's something stupid here that this looks wrong, but it's not. So those are actually composable coordinates because the right functions the wrong way. Right? So we're really gluing that one to the left of that one. Composition. All back in ruined category theory, basically. So what do we do? Well, the stuff to the left of, to outside of these two planes is no information at all. Right? You can recover it from knowing what this object is. You just cross it apart. So it's there because then I can talk about this subspace of non-compact manifolds, but it carries no information. So you can forget about the non-compact stuff. And this, of course, has some t associated to it, and this has some t prime associated to it. And what do we want to get? Well, you just glue the interesting parts of the coordinates together. So this should now go from 0 to t, and this should go from t to t plus t prime. And in between put something like that, and now you see why I asked for these to be standard near the walls, so that when I glue them I get a smooth manifold again. Okay. So as a set, I think it's obvious what you do. You just forget the stuff that has no information, compose them in the obvious way, and then extend the sugar to the outside again. And again, you can check that that's continuous and associative. Well, it's associative because we have these lengths built in. It's like taking more loops on a space instead of actual unit length loops. So it's strictly associative. And you can check that it's continuous in its topology if I told you what the topology is. Yeah?
It seems like you can easily just include identities in the structure. So identity equals 0.
Then you would be in a rather bad situation that a cylinder of length t could converge to an identity. And it's quite unlikely that that's going to be a good thing. It might be okay, but you don't. That's not the sort of thing that you really want, maybe. I would guess. You'd want the degeneracies to be cofibrations if you want a topological category to be an ordinary one, and that doesn't sound very good in that point of view. You could also allow them, but topologize it so that that can't happen. That's probably better. Oh, sorry. I wrote some map. Right, so the main theorem in this direction is using Galactus, Asenson and Weiss. And it says, oh, sorry, one last thing. C theta is the coordinate as n goes to infinity. C theta Rn. And the theorem there says there's a homotopy equivalence between the classifying space of this abortion category and this infinite loop space that I talked about last time. This thing I called loops infinity minus 1, mt theta. So if you don't remember what that is, I forgive you. It's, one time again, you suppose theta is a fibration, you pull it back over all the finite glass manions. On the finite glass manions, I call the map theta, which is the finite glass manion theta n. That has an n minus d dimensional bundle. On it, it has a d-dimensional one, canonically, but it also has the orthogonal one. You loop it n minus 1 times, and then you take the colimit, and then go. Okay? And in the picture, these sort of things you have to pass the different models of both sides all the time, but there's sort of a map that way that basically is given by this Pontryagin-Thom construction that I gave last time. Okay? So you like to think of this space as a point in it being a d minus 1 manifold with theta structure. Its Pontryagin-Thom map gives you a point here. And the coordinate in this space, its Pontryagin-Thom map gives you a path there, and so on. So there's a homotopy equivalence basically given by Pontryagin. Or whether the map is given by the Pontryagin-Thom construction, and the fact that there's an equivalence doesn't just immediately follow from that. And just want to point out one thing about this. So the spaces I talked about last time, the space of phetonol Wardisms of P with some structure. Well, what is that? This is just some subspace of the morphisms between theta and PLP in my category. Okay? That's not literally true because these things didn't have a length. You can wiggle this so that you build the length in, and then it's literally a subspace of this. Okay? And so, every point here gives you a 1 simplex in the classifying space, and hence you just have a canonical map, n theta p LP, to the space of paths in the base points to PLP on the classifying space. And under this equivalence, the composition is the map that I talked about yesterday. So it is just a Pontryagin-Thom map. Right, so in the strategy for proving the theorem I talked about yesterday is that this tells you something about the category of all manifolds with theta structure. And you might believe such a theorem ought to be provable because what property do all manifolds with theta structure have in common? I mean, they only have one property in common, which is they're manifolds of dimension d, and in each tangent space you have a theta structure. And you might express, because it includes all manifolds, it can't have any funny exotic phenomena of any particular manifold involved in it, and you might expect here to explain it in terms of the universal Grassmannian, which is the universal thing which is d-dimensional, and the universal theta structure of the Grassmannian. And indeed, that's not proof, but that's some of the reasons why this thing is not outrageous. But now we want to do something that perhaps seems a little more outrageous, is we want to say, I can take certain subcategories of this category of Gabordisms, well, I do restrict the manifolds down, and I can prove that they have the same classifying space. And hence I know what the classifying space is, it's this. And if you can do this for a small enough subcategory, you get down to a situation, suppose you can get down to a subcategory that just has one object, like a sphere, and Gabordisms from a sphere to itself. Then that's just a monoid. And there's a fantastic tool called the group completion theorem that tells you how the homology of a monoid is related to the homology of loops on its classifying space. It says that it's a localization of the homology of the monoid. And that's the sort of thing we want to do. We want to get down to a really small category so that the homology of B of that category is expressed in some simple way in terms of the homology of its morphism spaces, which are the things we're interested in. And then show that that smaller category is equivalent to the bigger one. And hence you know where it is. That's the strategy. This has several steps. So I want to explain what the intermediate categories are, so you don't go all the way down to the monoid in one go. So there are various intermediate categories. So the first one is I want to fix a manifold L inside minus 1, 0, cross R, n minus 1. And in my objects, remember, I thought of my objects as being inside Rn. And what I want to do is I want to fix an L that tells me what my objects have to look like on the lower half of that space. So this is going to be an L here. So this is a d minus 1 manifold fluid boundary. And fluid structure. And then I just want to take the subcategory where all of the objects have to contain L. So the objects are inside this space and they have to contain that submanifold. And all the morphisms have to contain L cross R. So let C theta L Rn, the subcategory of C theta Rn, be the subcategory where objects M, Ln have M intersect with this half space equals L. So not only do they have to contain it, but under here they have to be it. So everything else is contained in the upper half space. So as theta manifolds. And similarly, morphisms W, LW, T, I guess, remembering the length, have W intersect R cross n-0 cross R n-1 equals R cross n. Okay, so the picture is that objects look like this, they contain L and then they have some other stuff up here. And the morphisms are completely standard on the bottom and then have some other stuff. And of course they also can extend outside, but I haven't drawn that because it has no information in it. Okay? So they're standard on some little bit of the manifold. So that's the first smaller category that shows up. And I think I've put on the exercises that you should show that the inclusion of this category into the bigger category is an equivalence. That one, this is actually, this one you can do by category theory. The other ones you can't do, you have to do by some geometric argumentation. For any L. For any L. Yes, for any L. The trick is to produce a function the other way and show that they're adjoint. And then use this theorem, and the junction between functors gives a homotopy between maps on this space.
Also, so the classifying spaces are like all the top categories themselves.
No, it's the classified space. In this case, the categories are, there's a junction between them.
Yeah.
So they don't have to be equivalent.
Said the categories were
No, sorry. If I did, I meant the classified space. Okay. So the second one is C theta L kappa. It will be a subcategory of C theta. So whenever I don't write Rn, I mean I take the limit over n going to infinity. So this is the full subcategory. No, sorry, is the subcategory with the same objects and a morphism MW from M to M prime is in this subcategory. If and only if W relative to its outgoing boundary is kappa connected. Okay. So when I'm writing this, I'm silently always passing to this model now, where you don't have the stuff outside. Okay, so I just think of it as a complex model. So I mean, the cobordism relative to its outgoing boundary is required to be kappa connected. Okay, so if kappa is -1, this is a whole category. If kappa is 0, then every point in the cobordism we have to be able to find a path to the outgoing boundary. Okay, so for example, that is not in the category with kappa equals 0. Not in the category. Okay. And lastly, C theta L kappa map L. Unfortunately, I can only handwrite one font of L, so that's distinct from that. Otherwise, it looks like a 1 or something. So I can try to.
I mean, at this level of detail, you can just skip the L for the tangential structure. Say it's there.
I suppose that's true.
Also, the alphabet has another letter.
No. That's surprising. No. So that's the subcategory. So this is the full subcategory. On those LM, such that the map LM from M to B, and here I'm being a little bit sloppy in a way that I often am, so when I have a bundle map, it induces an underlying map between spaces, which I use the same letter for. Okay? So that's a bundle over B, this is a bundle over something, and I get a map of spaces as well. I use the same letter. So the underlying map is L connected. Okay. Now this looks a little different in flavour. B and C look a little different in flavour, but let me just point out that in practice, you choose L so that L to B is n-1 connected. L plus 1 connected, sorry. And if you've done that, then this condition is the same as saying that M is L connected relative to L, which it contains. So this is equivalent to ML is L connected. Which seems more natural somehow. So, but this is the one that's easier to work with. And one more category, but I won't talk about this one in detail, but I'll tell you what it is, because it does play.
Extensions in practice. The dimension of L is somehow.
I mean, you get to choose L, for example, and you get to choose theta, and you get to choose all these things. So when you actually want to apply the results I'll talk about, you choose B so that the map from L is highly connected. For example, if it's not, you replace it by the Minkowski stage of that map, so that it is.
Okay. We saw that last time.
Right.
Stages. Okay.
And so finally, D. This is something you can only do when D is 2m. Then, i.e. when D is even. Then I look at the objects of this category C, theta, L, n-1, n-2. So let's think about what that means. So the morphisms are n-1 connected relative to the outgoing boundary, and the objects, let's suppose that in this situation, the objects are n-2 connected relative to L. So that means you can basically build these manifolds from L by attaching n-1 handles and higher. Okay? And we'd like to go one step further and say you can construct them by attaching n handles and higher. Now, because sometimes connectivity doesn't translate into handle structures all the time, so it's better not to work with connectivity, but to work with something like handle structures or work with just some distinguished class of manifolds as the objects that you want. So you can fix a subset or a collection of path components of the objects of this category, and then you just define C, theta, L, n-1a to be the full subcategory of those. So for example, A could be things which can be obtained from L by attaching n handles and higher. That would be a class of things you might want to choose. It could also be things that are n-1 connected relative to L, and if L is simply connected, those will be the same, and if it's not, then it might not be the same.
Why does this only work in even dimensions?
Oh, I guess I could say this definition anywhere, but I'm only going to want to use it in even dimensions. So, yes. It's a good trick. I forget sometimes that you are allowed to define things for which you can't prove theorems, I suppose. Okay, and then the main technical work that goes into this is the following. So this is the main technical results in this paper with Galactus that I mentioned. Is as follows. D is 2n is at least 6. Theta is spherical. L and the structure on it is chosen so that these two things I said are true. LL to B is n minus 1 connected. So that's one condition. And the second condition is that L itself is built only using relatively small handles. So L has a handle structure using only handles of dimension less than n minus 1. Of course, with that you can guarantee that by attaching handles to make it true. You don't have to have n handles to make something be surrogated into n minus 1. And finally, A is a suitable class. Which is a bit technical to say that which is satisfied, so let's just say that. And now you have a load of inclusions between all these categories. N-1A is a subcategory of B, C, L, N-1, N-2, which is a subcategory of B, C, theta, L, N-1, N-3, all the way to E, C, theta, L, N-1, -1, and that is no condition on the last thing. Saying something is -1 connected is no condition, so this is B, C, theta, L, N-1. Then that goes to B, C, theta, L, N-2, and so on. To B, C, too excited. B, C, theta, L, -1, which is B, C, theta, L, and that goes to B, C, theta. And these are all homotopy equivalences. Then blah are all homotopy equivalences. And then by this result I mentioned down here, you also know that that loops into n-1 and g theta, and so you know in a sense that that's something constructed just out of algebraic topology standard tools, Thomas spaces and bundles and things like that. So you know the homotopy type of this much smaller category inference. Yeah?
I really read that part over there. So the first space has superscript n-1 and L.
And A is this class that I allowed to fix.
Yeah. And the next one is n-1 and n-2.
So yeah, so the last, apart from this first thing, which is a bit exceptional, then the last second coordinate goes down until it's -1, and then the first coordinate goes down until it's -1. And then you forget, lastly you forget this L. Oscar?
Do you use the fact that highly connected in-dimensional manifolds with highly connected boundary are exactly handle bodies?
So again, that
Highly connected manifolds with highly connected boundary.
so
They are exactly the handle bodies you obtain by only.
we don't use that for this because the boundary itself doesn't have to be highly connected. L could have fundamental group. Everything inside contains L and is highly connected relative to L. So in fact the boundaries don't have to be highly connected. The morphisms have to be highly connected relative to their boundaries, that's true. But things don't have to be absolutely highly connected. This is sort of relative thing. You can use things like that when you start applying this result to understand how small a category you've built for some choices of L and A and so on.
But if your theta, if your space B is n connected or n-1 connected, then
Right. Because L looks like B in some way,
Yeah.
so yeah.
So when L is a disk, then no.
Okay, so let me just assure you that once you've proved that all these are homotopy equivalences, then you can use something that's very much like the group completion theorem if you've chosen your A so that this is small enough. you might have chosen A so that this only has one object, in which case it's a monolith, and you can just apply the group completion theorem. And in the case that the example that I gave of this thing called theta n, and you get connect sums of Sn cross Sn, for that structure you can just take A to be the object given by the 2n-1 sphere, and that's it. And you can really get down to a monolith, and you can apply the ordinary group completion theorem. More generally, you need a sort of group completion theorem for categories, which is also something sort of well known. So I want to talk about that because if I do talk about that, then I won't mention surgery at all in my course of lectures, and then I'll feel a bit bad. So I want to talk about how you prove all of these intermediate sort of things, tell you some of the tools involved in that. So I'm going to have to skip group completion. So the point is first to introduce slightly modified models for all these classifying spaces, which are also simplicial realizations of simplicial spaces, but which are don't come from categories. And that's why, I mean, it's because of that you're really proving something about the classifying space and not about the category itself. It's because you're passing to this model that's not a category, and you're using that to work with. So you take a model for B, C, beta, L, L, called X bullet kappa L, so it's a simplicial space. Bullet is a simplicial degree. I guess it's really the realization of that. Defined as follows. So let's see. So P simplex. All the other theta and L are the symbols for the notation because that doesn't change, but kappa and L change. A P simplex is the following sort of data. Firstly, it's P plus 1 real numbers. And secondly, it's another P plus 1 positive real numbers, called epsilon, and hence they're small. And thirdly, let me just draw it. There's going to be a condition which is that these numbers have to be in order and their differences have to not overlap. So you get a load of intervals.
Didn't you say that you get P plus 1 A's?
Good, yes. So this is going to be the interval A0 plus or minus epsilon 0, A1 plus or minus epsilon 1, so on. And there's going to be conditions that say these are disjoint intervals. And the third bit of data is I want a submanifold of from A0 minus epsilon 0 to AP plus epsilon P. So it doesn't extend beyond the walls, it only goes up to the walls. So let me draw that. And you notice that the projection map to R is not required to consist of regular values inside. I'm allowed to have critical points. Okay. So there's some. So basically, these intervals are my replacements for my walls. And my walls were supposed to be regular because they had to intersect the manifold all the time. And what I want to do is I want to thicken my walls up to be a little continuum, and the property that it intersects in a manifold doesn't have to hold everywhere. Well, you can pick some bad slice that goes through this point, and that's not a manifold. But it has to hold to almost. Let's just say it has to hold almost everywhere. And so this is the third bit of data W and L W of this form. Okay, such that various things hold. The first one I've already said is that it's included just in its interval. The second one is that W agrees with A0 minus epsilon naught AB plus epsilon P cross L, where it should. So we've got an R cross minus 1, 0 cross R minus 1, something. So in my picture it doesn't contain an L, but there should be some sand bits at the bottom somewhere. The third thing is that all these things are in order, but I said that already. And the important points are, so my numbering jumps from 1 to 4 because some of the things I've just in my picture. is that for any pair of numbers in the union of these intervals, okay, so I can say T0 in here with T1 in there. Which are regular. Okay, so there are values that aren't, but for any pair which are regular, so for example, that one and that one, I get a cobordism, and that cobordism has to be kappa connected relative to the top. So every way I have of making an actual cobordism starting in these intervals has to be of the sort that had to be allowed before. So the cobordism, sort of W restricted to T0, T1, is kappa connected. Well, W restricted to T1. And then there's a similar condition on objects. For any regular T0 in this union, W restricted to T0 mapping to, how do I say it? Yes. W to T0 mapping to B is L. Okay? So what I've sort of done is I've loosened up the situation, so I don't have an actual object in the category, which is not a category anymore. I have a little range that tells me these things that you're allowed to think of as objects. Okay? And the conditions have to be satisfied for any choices I make there, but there are allowed to be some elements in that range which are not manifolds. I mean, it's allowed to have critical points in that range. Okay?
I have a curious question. What are conditions 2 and 3?
The things I drew, like A0 plus epsilon naught is less than A1 minus epsilon, things like that. Sorry, it's not L connected. Did I say L?
There's the big L is lost a bit, I think, in the picture.
No, it's not that. Sorry, I misstated C at the beginning, and then I carried that through. It doesn't have to be L connected. It has to be is mono on I less than or equal to L. This has to be injective. But again, if you assume this condition, it's already surjective as well, so it'll be self-connected. And this is the condition that we have on what we actually want to apply. And so here, similarly, you don't say L connected, you say mono. And for all base points, if you're bothered about base points. Okay, now these things look, I hope, similar enough. The proportion category in this looks, they're not completely wildly different objects, right? It's not completely obvious how you map from one to the other, and in fact there's not a direct map, you have to go through some zigzag in between. But they don't seem, I'm just going to assert that they're models for each other. Okay? And the point of using this model is that I'm a bit free to start wiggling my manifolds around. You see, in the cobordism category model, the slices always have to be regular values. So I can't possibly grab a bit of manifold from one cobordism and put it into the other one. Because at some point I have to move through this wall and then I make a critical point. In this model, I can continuously take a bit of manifold here and put it through that way. And if I don't make some, if I do it in a nice theorem, I make Morse critical points all the way through, that'll be fine. Because at some points there'll be a maximum and it won't be allowed, but then there's no condition on those slices. I only put conditions on things that are smooth, on the slices that are smooth. Okay? So this lets me allow the different cobordisms to talk to each other and to push things around more freely. That's the point of this instruction. So now let's give an example of how you use this. Let me do D as 2, or it'll work for any D, but the pictures will be D as 2. I want to compare exponent 0 minus 1 with exponent minus 1, minus 1. So when it's minus 1, minus 1, these are both empty conditions. Okay, so it's just arbitrary manifolds that have these walls and so on. But when it's 0, minus 1, my morphisms are required to be 0 connected relative to the outgoing boundary. So that means however I make the cobordism, it has to be 0 connected. Okay? So this is not in that space, even before I did this. Right? Because if I cut it with that T-rod, and I have this point here, there's no path to the outgoing boundary. Okay? So there are some slices that are good. If I cut it there, it looks alright, but it has to hold everything. So this isn't in the space. And so let me try to explain why this map is surjective on pi 0. Why I can take this thing that's not in space, and I can do something to it that's allowed in this space, and get into the subspace. And in order to do that, let me just draw a smaller picture so I don't have to do. And suppose I just have two sort of intervals, and let me suppose that the failure is this form. Okay? You can have something like that if you want as well. So the problem here is that if I'm on this component, I can't get to this end. That's why it's not in the 0 category. So this cobordism, however I slice it, is not in the is not going to be 0 connected to the upper end. Okay. So there's one obvious way you could fix this. If you get this match on, you could drag it through there. What? So, ta-da, I proved it's selective on pi 0. Now, that argument does not generalize. You will not be surprised to learn. You need to do something clever. And the reason is, suppose we had over here, so this is, here I've got two walls, I'm going to point on a 1 simplex in this space. Suppose I'm going to point on a 2 simplex, and I've got something over here. And suppose the one I've got over here is already good. Yeah? Then when I do this proposed move, all I do is move my problem around. I've now got a good cobordism, and I've one that what used to be good, I've now made bad. And if this thing is going to work in families, you have to not do that. Okay? So what you do is you don't pull it up, you pull it down. And that doesn't seem like it's gaining you much, right? You put it down in the following way. It's a 3-step program. First you pick a little disk in here somewhere. Okay? And now I'm going to write a standard model that starts with a disk, and because we're in R-infinity, I'm going to be able to glue my standard model in. Because everything is sort of, if I embed it generically, it misses everything else. So I start with a standard disk, and this dotted line is the rightmost dotted line, so like infinity. Okay? And I imagine having another disk to the other side of infinity. Okay? And I take the middle of my disk and I pull it down that way. So there's also, down here, there's a minus infinity, there's the lowest one. So I first take the middle of the disk and I pull it down here, and that gets me to a situation that looks like that. Okay? I also take the middle of this disk and I pull it down, and I put it through the middle of that one. Okay? So that's given, I've just described a path from that situation to this situation. Okay? Now I'm going to describe another path from something else to this situation. Then I'm going to do that path and the inverse of the other path. Okay? And the other situation is that. How do I get from there to there? I take this circle and I pull it down through the middle of that. And if I do that, I arrive at the same situation. Right? And it's important that I've been a bit vague down here, because here they don't agree. But the stuff that happens outside these walls isn't real. It's not, that's something I've made up. Right? My manifolds aren't even defined outside of these walls. So I can pull stuff out there, change it, and then bring it back on. Okay, and that's exactly what I do. So this gives me a path from that situation to that situation. And if I do this in this setup, it has the effect of, at time 1, it moves on something like that. Okay? But that's okay. The other thing at time 1 also works. Just taking it and pulling it up ended at the same thing. Right? That was my other proposed strategy. I just pull this point and I pull it up, and at time 1 it had the same effect. But at intermediate times, the other one looked like that, which is not highly connected once the outgoing boundary. And this one at intermediate times looks like that. Up here, right, at some point when you pull that down a little bit, it's still highly connected relative to the outgoing boundary. And in fact, at all times, it stays highly connected relative to the outgoing boundary. So by doing this move, you don't break this property of other things. That's one key step. So it's a move that doesn't break good things that you already had in your life. There's another very important point, which is that if I'm going to do this in families, at some point I have to pick where I'm going to do it. Okay? And if I've got a family of coordinates over some parameter space, then that starts to seem a little bit difficult. And the very important point is that if suppose I pick 2 disks and I do the same move on the 2 different disks, okay? And up there, that's also good. I haven't made it worse by doing it twice. I did it once and I made it pathing it relative to the outgoing boundary. If I do it again, well, it stays pathing it relative to the outgoing boundary. And I can linearly interpolate between doing these 2 things if they're disjoint. Right? I can do one of them, say the top one, then I can do the second one, then I can undo the top one, and that gives a path between them among things that are highly connected relative to the outgoing boundary the whole time. Okay? And so what you end up doing is that you don't actually have to pick a preferred point everywhere that you're going to do your surgery. You can choose lots of points all over the place and do it lots of times, and you'll still fix things. And that's what makes this work in families. Okay. Right, so that's the first move, and this is what you do to make the morphisms be highly connected relative to the outgoing boundary. Okay? So very technically what you actually do is you build a bisimplical space where a PQ simplex is a P simplex in X, so it's a thing cut up into P plus 1 pieces, and it also has Q plus 1 bits of surgery data, wherever you might need them. And it's designed so that if you do that surgery, you're in a good situation. All you now have to show is that this space is equivalent to X by the map that forgets the surgery data. Okay? And that uses some, because everything is actually topological, that's actually a bit involved. If everything was topologized discretely, that would just be the fact that you've sort of got a poset. You've got a simplicial complex of surgery. Suppose you fix a manifold, P simplex with P plus 1 bits of surgery data, and they have the property that I can always find another one, which is disjoint from any finite set of surgery data. Why is that? Because I'm picking points in the manifold, and the manifold has a positive dimension. So given any finite collection of points, I can find another one that's disjoint from them, right? And if you've got a simplicial complex that has the property that for any finite collection of vertices, you can find another one that spans a simplex with all of them, well, it's contracted, or weakly contracted at least, because you can cone off everything you like. And so the way you prove this sort of thing is just a topologized version of that, which is technically more difficult, but not conceptually more difficult. So the fundamental point is that the data, if you pick it generically, it's disjoint from each other. And that lets you do this coning off. So that's one of the moves. Now let me talk about the moves that makes the objects be highly connected, or the map to L at least be injected. So, suppose we're in a good situation, so really what we're trying to do is make the objects highly connected. When have I... Sorry. Is that a clue?
It's sort of -2 minutes point.
Let me draw some pictures and wave hands a bit.
I have a question about these points where the surgeries.
Yeah.
You do take care of higher non-connectedness,
Right.
but then the
Higher
points
things.
are loops or
They're loops and so on, but we only, if you look at my thing here, we're only ever doing surgery strictly below the middle dimension. So picking surgery data at random will be disjoint. Yeah.
so you couldn't push it above at all, because then you would have all kinds of problems to solve.
Right. And in fact, the reason why one would have a similar theory for odd dimensions is exactly that. So let me just explain very briefly what we do for objects. And it's important that for objects you suppose you've already done the morphism. Okay? let's suppose that I'm in a situation x equal to 0, 0, go into the space I just got into, namely 0, minus 1. So here the morphisms are highly connected, but the objects aren't, and we want to get to a situation where the objects are partly connected. Okay? So a typical thing would be this. Okay? The morphism is 0 connected relative to the top, but this object is alright, but that object is not alright. Sorry, here. Yes. I don't have slices, do I? This goes all the way through. So what do you do there? Well, what can I, if I've got two circles, so I suppose I want to make it connected, the easiest way to do that is to make the connect sum. So if I pick, in some slice, if I pick 2 points, and I do a connect sum between them, I would have made that slice be path connected, by definition. Right? So that's okay, I can do that. That gives me a new point in this space. But I want to show it's surjective on pi 0, so I have to show it, I can connect it by a path to my other point. Right? So how do I do that? Well, using the fact that everything's already 0 connected relative to the top, I can move where I do this connect sum off that way. So I pick some parts, and then I take this handle that I attach, and I go like that, and then it's not attached anymore, and I'm back where I started. Okay? Now, you have to worry about several things, like, does it preserve the fact that the morphisms are connected and so on, but it does. In fact, there's a, yeah, right. And so again, what's the surgery data? Well, in this picture, the surgery data is an embedding of S0, and you also have to pick these parts, and you have to pick them to be disjoint, because if I attach 2 handles here, I need to be able to slide them off sort of independently of each other. When I'm moving in my simplicial complex, I need to interpolate between them. And that's now a bit more difficult, because now the surgery data are 1 manifold and a 2 manifold. And those are not generically disjoint. And there you have to go to a certain bit of extra trouble to do a sort of half Whitney trick, or Whitney trick against infinity. So in a non-compact manifold, when you're doing disks and not spheres, you can always make things disjoint. Just by, you think of it as being, you reflect it in that side, and then you do have a Whitney disk. Because you just created a critical point of the opposite index, and then you do the Whitney trick there, and then you remember that all this stuff actually didn't actually matter, and you've in fact done what you want. So in this case, it's not completely for free when you come down to doing surgery sort of in the middle dimension. It's not just general position that buys you it, you have to do some Whitney trick stuff. Let me just stop there.
Topology on this, I'm going back to the very beginning. Could you somehow axiomatize the relevant properties of that topology?
The topology on the sheaf side D?
Yes.
Yeah, I don't know. It sort of has a smooth structure, which is very easy to axiomatize. You know what a smooth map into it ought to be. So what theology or something has one of those things. So there's no ambiguity about what a smooth map into it should be. So I don't know. So we prove, for example, in the topology we construct, continuous maps have smooth approximation. That's one of the technical things one has to prove. Yeah, and the smooth structure is unambiguous. In a smooth manifold into it ought to be a submersion. But I don't know if you could axiomatize the topology, and I'm likely to do it on the spot.
In your main technical result, there is this suitability condition on A.
So which one?
The A has to be suitable.
It has to be suitable, yeah.
Do you have a condition which is telling you what is suitable? I guess the idea is, of course, the right-hand side you often can compute it, right? That's we're talking about these.
So it's nothing. It's not mysterious at all. So suppose we fix one manifold and declare that to be the class A. We're going to get a little bit stuck because in here there might be objects which are not coordinate to that manifold, and so this isn't going to be surjective on pi 0. But that's the only thing that goes wrong. So if you pick A to be big enough that it contains every cobordism class, then it's satisfied.
Okay.
It wasn't that difficult, I could have just said that. Yeah.
So you rather want to have something which has only one object in it. For this.
Right, so then you do a trick. You take A to be the class of a manifold M and all manifolds not cobordant to M. That contains all cobordant classes, you will agree?
Yeah.
And because M and the ones not cobordant to M are not in the same path component, when you take the loop space, which you're going to do in a minute anyway, you only see the manifold that you had.
Okay. So in the end, you answer some questions about your favorite manifold M.
Yeah. Yeah, it's convenient to set it up this way because in general you don't just want one manifold and self-cobordism to that. You want these P10s. So you don't necessarily want it to be a monoid. It's more general to have something slightly bigger.
Okay.